Hi and welcome back to maths class. So today we're looking at differentiability of a function, and specifically we're going to look at how do we know if there are any parts of our function which are not differentiable. Now, just a quick bit of revision. We've just been looking at continuity, and what we discovered about continuity is that a function is going to be continuous at any point where x equals a if f of a exists at that point, if the limit of as x approaches a of f of x exists, and if those two things are the same. And we looked more informally at continuity, at looking at things like jumps and asymptotes, and any time where we can clearly see a gap in our function, then our function is not continuous. So today we're looking at differentiability. And the question we want to be able to answer is, how do we know if a function is differentiable, particularly at a point? Now here is the formal definition. F of x is differentiable at x equals a if the limit as h approaches 0 of f of a plus h minus f of a over h exists. Now you should be able to recognize this. This is the formula for the secant from the 2 points p and q when we originally defined the derivative of a function, but instead of a here, we had x, and then once we make it the limit as h approaches 0, that's no longer the secant, that's now the gradient at the point x. Now we've substituted in a here because we're looking at the point where x is a, but this is very specifically the definition of when the function is differentiable. However, we're not always going to look back at this. What we're really looking at is, does the limit of the gradient from the left equal the limit from the right? And is the function continuous at the point x equals a? So if I look at my graph and I can see that those two things are true, then my function is differentiable. Visually, what that means is that my graph is going to be continuous and it's going to be smooth. Now the continuous part means there's no gaps. I don't lift my pen off. The smooth part means that my gradient doesn't change suddenly with a sharp corner. And I'm going to illustrate those two things, continuous and smooth, using this example. So my first example is if f of x equals x squared plus 2x plus 1 for x is less than or equal to 0, and f of x equals x plus 1 when x is greater than 0. Now this is a piecewise function made up of a quadratic function and a linear function. And my question is the function differentiable at x equals 0? Now, if I examine this looking at the derivative as I approach from the left and the derivative as I approach from the right, x equals 0 is the boundary point between these two functions. So from the left, I'm going to have a different derivative function than I have from the right. From the left, that is for x less than or equal to 0, I'm going to have this function, which has a derivative of 2x plus 2. So the limit as x approaches 0 from the left of x dash of x is going to equal 2. When I substitute in x is 0 here, I get 2. From the right, f dash of x equals 1 everywhere. It's going to be a straight line, so it's got a constant gradient. So the limit of x, as x approaches 0 from the right of f dash of x equals 1. So what I can see here is the limit from the left does not equal the limit from the right. So the function is not differentiable at x equals 2. Sorry, at x equals 0. Now, let's have a look at what that looks like visually. There's the graph of this function. I haven't marked any key points, but what I'm most specifically interested in is this point here. This is a continuous curve. When x is 0, I substitute that into the first function, I get 1. In the second function, I also get 1. So this is the point 0, 1. It is a continuous function. I can draw it all the way without taking my finger off the graph. However, it's not smooth. I can clearly see a kind of sharp corner there, and a sharp corner indicates that the gradient as I approach from the left is not going to be the same as the gradient as I approach from the right. And I can see that the graph is very steep here as I approach, and it's less steep as I approach from the right. Now, just to really emphasize that, here is the derivative function. My derivative is going to be 2x plus 2 for f dash of x for x is less than 0, and f dash of x is going to be 1 for x is greater than 0. Now, this derivative function is not continuous, and that's really what we're looking for. If a function is not differentiable at this point, then the derivative function will not be continuous at this point. So for x is less than 0, I have this straight line function. For x is greater than 0, I have a horizontal line. For x equals 0, the derivative is not defined. Okay, we're going to look at some further implications of this, and I'm going to start by looking at f of x equals the cube root of x, and the question is it derivative for x is an element of the reals? Because this function exists for the whole domain of the real numbers, but where is the function not differentiable? If I look at the derivative function, if I rewrite this as x to the power of 1/3, to find the derivative, I multiply it by 1/3, I subtract 1 from the power, the derivative is 1/3 x to the power of negative 2/3. Now I can rewrite that as 1 over 3x to the power of 2/3. In other words, my x is a denominator, which means x cannot be equal to 0 for the derivative function. And if I look at a graph of the cube root of x, that's what it looks like. It's the inverse function of x cubed. I can clearly see that briefly here it has a vertical gradient. Now, a vertical gradient means it's not differentiable. If I was doing straight lines and I asked you what is the gradient of a vertical line, you would say undefined. And that's exactly what's happening here. The gradient is vertical at this point, which means that the gradient is undefined. So the function is not differentiable at this point. In fact, it's only differentiable for x is an element of the reals excluding 0. I can differentiate it everywhere else, but not when x is 0. There's one other implication that we want to look at. Here's I've chosen a nice easy function for us for f such that over the domain of negative 2 to 2 maps onto the reals, f of x equals x squared. Find and sketch the derivative function. Okay, it's a quadratic. I can do this. F dash of x is going to be 2x. It's a nice straight line. But first, let's look at the original function and let's sketch that. So this is x squared, and here is 2 and negative 2. So this is going to be the point 2, 4, and this is going to be the point negative 2, 4. And those 2 points are included in my domain. So closed circles. All right, that's my quadratic function. But remember, if we go back, let's just go back to what we originally said about when a function is differentiable. The limit of the gradient from the left must equal the limit of the gradient from the right. Now let's look at the endpoints of this graph. As I approach this point, negative 2, 4, from the right, I can see that I have a gradient. But I cannot approach from the left because the graph finishes. Therefore, my graph stops being continuous after this point, which means that on this point, I'm not able to differentiate because I'm not able to establish a limit of the gradient as I approach from the left. Therefore, f dash is going to be this. Okay, and when I sketch it, I'm going to show, what have I got? 2x. I'm going to show open circles here. This is going to be the point 2, 4. This is going to be the point 2, -4. Open circles at the end of the domain, because on the end points, this graph is no longer continuous. Therefore, it's no longer differentiable. And that's the end of our video on differentiability.